Okay, hi guys, we're team 11 and so we're in charge of question 1. So in order to obtain the palm head and the efficiency curve, it's basically given by the data. So what you really need to plot is to obtain it from the data here. You plot the flow rate versus the palm head and the flow rate versus the palm efficiency. From there, you obtain this green curve, which is the efficiency curve, and the palm head curve. So what we really need now is the system curve. In order to obtain the system curve, the equation that we need to use is HA equals to Z2 minus Z1 plus HL. So as listed here, you can see we have all the data given, and what we need is the friction factor F. So in order to obtain the friction factor F, this equation is to be used. F equals to 0.25 over log 10 blah blah blah. So in order to obtain a friction factor, you need to have the Reynolds number as well. So in order to obtain the Reynolds number, this is the equation that we use, the typical Reynolds number equation, V times D over the kinematic viscosity. So with the Reynolds number, you can find the friction factor, and with the friction factor, you can find the system curve, and you just need to plot it into Excel. You get a friction factor with the equation, and you plot it versus the flow rate. So this is how you actually get a system, palm head, and efficiency curve. Okay, as for question 2, in order to find the operating point, it is basically the intersection between the palm head and the system curve. So this is basically the operating point, which is around 15 liters per second. So with this operating point, we can obtain the efficiency by just pulling it all the way up here using your operating point, and you get approximately 85%.
83.
Yeah, 83%. So this is basically how you get those value. Alright, as for question 4, they're asking what's the power delivered by palm to the fluid. So basically we're just using this equation, gamma Q times HP. So gamma is the specific weight, which is 9800 Newton per meter cube, and Q you change it from liter per second to meter cube per second, which yields 15 times 10 power of negative 3. And as for the HP, we get it from the graph, which is basically the operating point, and you can get the value is 6.55.
The unit is meter.
Yeah, the unit is in meter. So essentially the answer, you just gonna multiply this up and you get 0.96 kilowatt. So as for question 5, in order to obtain the power required to power the pump, basically what you need to do is to obtain to get this value that you obtain from question 4, the power delivered by pump to the fluid, and you divide it by the efficiency that you obtained from the graph earlier on. And so it's 0.96 kilowatt divided by 83%, and it comes up to be 1.16 kilowatt. And for 83%, basically it's equals to 0.83. So this is how you come up with this value, 1.16 kilowatt. So as for question 5, we're required to plot the MPSH required and actual versus the flow rate. So MPSH is basically the net positive suction head. So this is actually really easy. In order to obtain the MPSH required, well, it's actually given in the data here. So basically what we really need to do is to plot the required net positive suction head, the data here, versus the flow rate, the data given here. And this is basically how you obtain this data here, the blue curve. This is the positive net suction head required. And next, we need to plot the actual net positive suction head. And in order to plot those values, we need to put in this equation in it. So the actual net positive suction head is basically the absolute atmospheric pressure divided by specific weight, where you obtain this value, minus the elevation, 3 meter, and the sum of the head loss. It's actually F times L over D times V squared over 2G. And since in this question we are given the flow rate, so with this flow rate we can actually obtain the velocity here. So basically what we're really doing is to put in Q over A into this V equation here, and this is how we actually obtain the head loss. And this head loss equation is also shown in first question. And we get a minus the vapor pressure divided by the specific weight, and vapor pressure can be obtained from our hydraulics book, appendix part of hydraulics book. So with this equation we can obtain the actual net positive suction head. And what we really need to do now is to put this equation into Excel and kind of pull it down all the way, and you get all this data. So this is basically the actual net positive suction head. With this data, we plot it versus the flow rate, and this is how we actually obtain this kind of red pink curve here. So after obtaining the actual net positive suction head, we really need to obtain, according to question, we need to find at what point where cavitation actually occurs. So this is actually really easy by looking at the graph. As long as the actual net positive suction head is smaller than the net positive, required net positive suction head, that's actually where cavitation occurs. So from this graph, as you all can see, after this intersection point here, basically this is where cavitation starts occurring. So at what range it occurs is basically starting from this point, which is approximately 23, all the way to the end here. So thanks for watching, guys.